Hello everyone, my name is Hamed Mir. I'm a PhD student at Heriot-Watt University, and today I'm going to present my work on upscaling of the water alternating gas process from immiscible to miscible conditions. This project is supervised by Professor Arnes Koge. So let me start with a bit of background. WAG, or water alternating gas injection, is an enhanced oil recovery process where water and gas are injected in alternating slugs, and they play different roles. For example, water provides mobility control and increased area sweep, and gas has higher macroscopic displacement efficiency, especially under miscible condition. Compared to pure water flooding and pure gas injection, it has been shown that WAG has lower residual oil saturation and better sweep efficiency. That's why it has been applied in many major oil fields worldwide, especially in Brazil. Now, the transition between immiscible and miscible WAG is very important. In immiscible WAG, displacement is dominated by viscous forces and trapping of oil and gas is significant. Why I said viscous forces? Because in the 2D horizontal model I'm using, there is no gravity, and because of the model size, capillary forces are negligible. On the other hand, in miscible WAG, the injected gas mixes with the oil and removes the interfacial tension, and this improves macroscopic displacement efficiency. So, understanding this transition is critical for reservoir management and predicting recovery. Here you can see how CO2 is dissolved in oil phase from miscible to immiscible conditions. Okay, let's talk about upscaling. As you know, fine grid simulations capture small-scale processes like viscous fingering, but they are computationally expensive. And for history matching or optimizations where thousands of simulations are needed, fine models are not really practical. So upscaling reduces the fine scale model to a coarser one that's much faster. But the challenge is how we can reproduce the fine model results from the coarse model simulations. Here you can see the oil saturation of the fine and coarse models. In the fine model, we see details, fingers, and sharp fronts, but in the coarse model, they are smeared out. And obviously, the production curves are different from the fine model. So, the aim of this study is to develop a workflow for upscaling, which can mimic the fine-scale production data while reducing runtime. There are different ways to upscale: pseudo-function, transmissibility multipliers, or pseudo-real perms. Here I choose pseudo-real perms, or LET correlation in my case, because they directly control phase mobilities as well as breakthrough times and production profiles. Pseudo-real perms are also very flexible ways to consider small-scale displacement effects into the coarse-scale model without changing any grid property. So, as you see here, I use the 4-stage optimization workflow based on particle swarm optimization, or PSO, to tune the coarse scale model. The objective function here is the root mean square error, or RMSE, between production profiles such as oil recovery, gas production rate, and water production rate of the coarse and the fine models. Here are the stages. In stage 1, I adjust the real perm endpoints and the critical saturation. This step is very important because these parameters control where the real perms curves starts and ends, and they tuning them so we can control the breakthrough times and the initial shape of the production curves. In stage 2, I optimize the L, E, and T parameters for water and oil. These parameters control the shape of the real perms, so we can capture the slope of the oil recovery and water production. And in the next stage, I change L, E, and T for gas and oil. This step improves the gas mobility and helps to match the gas breakthrough and also the production rates. And finally, I tune hysteresis parameter, Lance constant, and the KRG reduction factor, or alpha. These parameters capture gas and water trapping during WAG cycles, which is essential for matching lead time water and gas production. At each stage, parameters are allowed to change around 20% of their initial values, while parameters optimized in earlier stages are only allowed to change by 5%. And by doing this, it prevents the optimizer from undoing the progresses made in previous steps. Now let's look at the results. Here you can see the production profiles, oil recovery, gas production rate, and water production rate. The black curves and blue ones are the fine and coarse models before optimization, and the red curves are the best match after the 4 stages. You can see that clearly the coarse model deviates, and the timing of the breakthroughs is different, the rates are not captured well. But after optimization, the coarse model follows the fine model very closely, and the breakthrough timing is well captured, and the slope of the production curves align much better. Here you see the real perm curves. The dashed lines are the original curves, and the solid lines are the optimized pseudo curves. You can see how the optimizer shifts the shape of the curves to match the production behavior. For example, lowering the gas real perm to delay gas breakthrough, or adjusting the oil curve to improve oil recovery. And here on the right, we have the RMSE values after each stage. The error starts at 1.22 in stage 1, decreases to 1.148 after stage 2, and drops further to 0.9 in stage 3, and finally reaches 0.796 after stage 4. That's about a 35% improvement overall. We can also compare the gas saturation after the first, third, and fifth cycles of water injection and gas injection, and how coarse model is able to capture the fluid movements and trapping effects. Finally, I'd also like to thank the sponsors for supporting this work, and thank you very much for your attention.